Yay! We're back to notes. I know it's not as exciting as in person, but you know what? We're going to make best with this. So just pretend you're looking at the board and that I'm writing right in front of you. We got this. All right, chapter 7. We are going on to the topic of linear momentum. Woo! Party! Momentum is actually a word that I'm sure you guys have used in your life. People say, the team's got a lot of momentum. They're going to be hard to stop. The idea that you guys have about momentum is actually correct. In physics, momentum is if a object with mass is moving with some velocity. Then it will have momentum. So when a team's doing really good and they've got a lot of forward momentum, they're going to be hard to stop. That means they've got, mass and velocity. The actual definition of momentum is literally just mass times velocity. The variable that we're going to use for momentum, we're actually going to use a p. So we're going to say that p equals mv. Momentum equals mv, mass times velocity. One thing that you guys should notice is that we have the arrows overhead again. This means that they are vectors. Sorry, there we go. Vectors. So direction does matter. You can have forward momentum, you can have backwards momentum, you can have north momentum. You need to worry about your direction when you're dealing with momentum. The other thing we can talk about momentum is what if we take our definition, we take our momentum equals mass times velocity, and we take the timed rate of change, which just means what if we divide by delta t? What happens is our delta p over delta t is therefore m times delta v over delta t. This is acceleration. So what happens is change in momentum over change in time is equal to mass times acceleration. Well, what else is equal to mass times acceleration? Force. So now we have this relationship between force and momentum, and we can say that the net force of an object is equal to the change in momentum over the change in time. This is actually how Newton originally wrote his second law. So how Newton's second law was originally written. So you guys were taught F equals ma. Well, F equals delta P over delta T is the same thing. Forces cause accelerations, well, forces cause change in momentums. So if you change your momentum over a period of time, you need a force to do that. This brings us to our conservation of momentum. So just like how energy was conserved, we can also say that momentum is conserved. Conservation of momentum states that a system cannot change momentum by itself. So unless a system is acted on by a net external force, the initial momentum of the system equals the final momentum of the system. So your PI is going to equal your PF. So what happens is if you don't have any net forces, you're going to have conservation of momentum. Your momentum does not change if your net force equals 0. So a lot of times in this chapter, we're going to have like car crashes. Car crashes is a great example of conservation of momentum. In the collision, the objects may change momentum, but the overall momentum initial is going to equal the overall momentum final as long as there was no external net force. And we can solve for cool things like what's the speed after. If we're talking about collisions in like the game of pool, what's going to happen to the 6 ball after the cue ball hits it. You can do that type of analysis with momentum. So if you have more than one object colliding or exploding, that's when you're going to use momentum. All right, let's do 2 example problems, and then we'll call it a day for today. So we have an example where we have water leaving a hose at a rate of 1.5 kilograms per second. What in the world is this? 1.5 kilograms per second. Well, kilograms is a measure of mass, and seconds is a measure of time. So that's not really anything other than mass per time. They're telling you that mass per time is 1.5 kilograms per second. They leave it with a velocity of 20 meters per second. So my initial velocity is 20 meters per second, and it's going to hit the car, which brings it to rest. My final velocity is therefore 0 meters per second. I want to know the force exerted on the water by the car. All right, well, I just told you guys we can use Newton's second law in momentum form to say, all right, net force is delta P over delta T. Well, momentum is mass times velocity. So it's mass times change in velocity over change in time. Well, look, mass per time is 1.5. Change in velocity is final velocity minus initial velocity. So we can figure out what that is. Delta V equals final minus initial, which is just negative 20 meters per second. So all we have to do to figure out my net force is multiply my mass per time, which is 1.5 kilograms per second, times my change in velocity, which is 20 meters per second. Therefore, my net force is equal to 30, and my units of force are newtons. So the car is exerting 30 newtons of force in order to bring this water to rest. In order to bring this water to rest, the momentum is changing over a period of time, so a force is required. This is an example where momentum's not conserved. We're using F equals delta P over delta T. We have a external force. That external force is 30. Cool. Now let's do an example where momentum is conserved. So in this case, we're going to have a Nerf dart whose mass is 50 grams, is going to be fired horizontally with a speed of 1,100 meters per second with the mass of 6 kilograms initially at rest. So we want to figure out the speed of the Nerf gun when it recoils. All right, so a very common example of conservation of momentum is this idea of recoil. I'm sure you guys have heard of recoil. If the Nerf dart is launched forward, the Nerf gun therefore will recoil backwards. This is because momentum is conserved. So your initial momentum is going to equal your final momentum. Well, initially, the dart is at rest in the gun. Nothing is moving. So the initial momentum is going to be 0. Afterwards, we're going to have the momentum of the dart, which is the mass of the dart times the speed of the dart, and the momentum of the gun, mass of the gun, speed of the gun. So initially nothing's moving. Afterwards we have the momentum, which is mv of the dart, plus the momentum of the gun, which is mv of that. Okay, so be careful with units. The mass of the dart has to be in kilograms, so 0.05 times the speed of the dart, they said, was 1,100 100 meters per second, plus the mass of the gun, which is 6 kilograms, times the speed, the recoil speed. That's what we're looking for. That's our goal. Well, that's the only variable, so I can figure that out. Therefore, the speed is going to equal negative 9.166 meters per second. Because the dart is fired forward, the gun will recoil backwards. That's why it's negative. Hopefully it makes sense that it's negative. The direction of the dart is the opposite direction of the gun. So we will recoil backwards. While I was doing this, I thought of one thing. I forgot to mention units. Let's go back to the first page. The units of momentum are kind of strange. There are 2. So units, we can either use, well, if it's mass times velocity, it's kilograms times meters per second. Or if we look at the other equation, momentum is force times time. If I rearrange this equation right here, delta P is force times time. So it's newtons times seconds. Those are the 2 units for momentum. So when you're solving these problems, you always need all of your values in kilograms, meters, and seconds, and newtons. So that's why when we were doing this example problem right here, I had to make 50 grams into 0.05 kilograms. I'm going to call it a day. I don't want to do too much. We're going to pick up here. We'll do notes again tomorrow. We'll do 1, 2, 3 more example problems tomorrow, and then you guys will work on some problems your own. So that's coming up, but for now, we'll call it a day. I'm not trying to overwhelm you guys. I'm trying to take it nice and easy and nice and slow. If you have questions, let me know, but hopefully this makes sense. Okay, have a great day, guys. Thanks for watching. Bye.